Welcome to the session on understanding vibration analysis with condition-based maintenance. Before understanding vibration, let us first understand maintenance strategies. Maintenance strategies are approaches used by organizations to manage and preserve their assets, equipment, and infrastructure. These strategies aim to ensure the reliability, availability, and efficiency of assets while minimizing downtime and costs. There are several types of maintenance strategies. Here are some of the most common types. 1. Reactive maintenance. 2. Preventive maintenance. 3. Predictive maintenance. And 4. Condition-based maintenance, also called proactive maintenance. Now let us understand them one by one. Reactive maintenance, also known as breakdown maintenance or corrective maintenance or run to fail, is a strategy where maintenance activities are performed only when equipment fails or breaks down unexpectedly. In reactive maintenance, maintenance actions are triggered by equipment failures or malfunctions. The primary goal is to restore equipment to working condition as quickly as possible to minimize downtime and production losses. For example, in a manufacturing plant, a critical machine suddenly stops working due to a mechanical failure. Production comes to a halt, and maintenance personnel are called in to diagnose and repair the issue. Once the problem is identified and fixed, production resumes. While reactive maintenance is sometimes necessary for addressing unexpected equipment failures, relying solely on this approach can lead to inefficiencies, increased costs, and operational disruptions. Organizations often complement reactive maintenance with preventive or predictive maintenance strategies to improve overall equipment reliability and performance. Preventive maintenance is a proactive maintenance strategy aimed at preventing equipment failures and optimizing the reliability and lifespan of assets. Preventive maintenance involves systematically inspecting, cleaning, lubricating, and replacing components of equipment at predetermined intervals. The goal is to identify and address potential issues before they escalate into costly failures, thereby minimizing unplanned downtime and extending equipment life. For example, in a manufacturing plant, production equipment undergoes preventive maintenance according to a predefined schedule. Maintenance technicians conduct inspections, lubricate moving parts, tighten loose connections, and replace worn components as needed. By adhering to the preventive maintenance schedule, the plant avoids unplanned downtime, maintains consistent production output, and prolongs the lifespan of critical machinery. Predictive maintenance is a proactive maintenance strategy that utilizes data analysis and condition monitoring techniques to predict when equipment failures are likely to occur. Predictive maintenance aims to identify potential equipment failures before they happen by analyzing data related to equipment condition, performance, and operating parameters. It relies on various monitoring techniques such as vibration analysis, oil analysis, motor current signature analysis, MCSA, thermography, and non-destructive testing, NDT, to detect early signs of deterioration or abnormal behavior. By predicting when maintenance is needed based on data-driven insights, organizations can optimize maintenance schedules, minimize unplanned downtime, and extend the lifespan of equipment. For example, a manufacturing plant implements predictive maintenance for its critical production equipment. Vibration sensors are installed on rotating machinery to monitor vibration levels continuously. An increase in vibration amplitude beyond predefined thresholds triggers an alert, prompting maintenance technicians to inspect and address potential issues before they escalate into failures. Proactive maintenance involves taking preemptive measures to maintain equipment in optimal condition and prevent unplanned downtime. By identifying repeated failures, organizations can minimize the risk of costly breakdowns, extend equipment lifespan, and improve overall reliability and productivity. When failures occur despite proactive maintenance efforts, root cause failure analysis (RCFA) is used to investigate the underlying causes and implement corrective actions to prevent recurrence. The key purposes of vibration analysis are: early fault detection. By analyzing vibration signals, technicians can identify issues such as imbalance, misalignment, looseness, bearing defects, and resonance, which may indicate impending failure. Condition monitoring. By regularly monitoring vibration levels and trends, technicians can track changes in equipment health over time and assess the effectiveness of maintenance activities. Predictive maintenance. By leveraging historical vibration data and predictive analytics, organizations can predict potential equipment failures and plan maintenance activities accordingly. Root cause analysis. By examining vibration signatures recorded before the failure occurred, technicians can pinpoint the underlying causes of the failure, such as bearing wear and shaft misalignment. The basic theory of vibration revolves around the study of oscillatory motion, particularly the repetitive movement of mechanical systems around a stable equilibrium position. It follows sine curve. The physical significance of vibration characteristics lies in their ability to provide valuable insights into the behavior, performance, and health of mechanical systems. Here's how various vibration characteristics are interpreted and their significance in practical applications. Amplitude. Amplitude represents the magnitude or intensity of vibrations, indicating the extent of motion away from the equilibrium position. Monitoring and controlling vibration amplitudes are essential for ensuring equipment reliability and safety. Frequency. The frequency of vibration indicates how rapidly a system oscillates about its equilibrium position. By analyzing the frequency spectrum of vibrations, engineers can identify the root causes of machinery faults, such as unbalance, misalignment, looseness, or bearing defects. Phase angle. Phase angle relationships provide critical information about the spatial distribution of vibrations and can help diagnose the source and propagation of mechanical disturbances. Analyzing phase data enables engineers to pinpoint the locations of faults, identify mode shapes, and optimize structural designs to minimize unwanted vibrations. In vibration analysis, displacement, velocity, and acceleration graphs are essential tools for understanding the behavior of vibrating systems. When plotting displacement, velocity, and acceleration graphs in vibration analysis with frequency on the x-axis usually in Hertz and vibration sensitivity on the y-axis, the interpretation slightly differs. Displacement refers to the distance a structure moves or vibrates from its reference or rest position. Velocity describes the rate of change of displacement. It is the measure of the speed at which the mass is vibrating during its oscillation, while acceleration measures the rate of change of velocity. The greater the rate of change of velocity, the greater the forces on the machines. When frequency is on the x-axis and vibration sensitivity is on the y-axis, displacement, velocity, and acceleration graphs provide a detailed understanding of how the system responds to different frequencies. Analyzing these graphs helps identify resonance frequencies, critical frequencies, and potential issues in the vibration profile of the system. In vibration analysis, there are two different approaches to analyzing and understanding vibration signals. These are the time domain and the frequency domain. Time domain analysis focuses on understanding how the vibration signal changes over time. Common time domain techniques include waveform analysis, peak-to-peak analysis, and RMS, root mean square, analysis. Frequency domain analysis focuses on decomposing the vibration signal into its constituent frequencies and their respective magnitudes. Common frequency domain techniques include FFT, fast Fourier transform analysis, power spectral density (PSD) analysis, and frequency spectrum analysis. Frequency domain analysis approach: vibration analyzer performs mathematical techniques such as FFT, fast Fourier transform, to convert time domain to frequency domain. FFT method shows the relationship of discrete frequencies and their amplitudes. This separates individual frequencies and detects how much vibration at each frequency. A typical fast Fourier transform spectrum graph is a representation of frequency domain data derived from a time domain signal. As you can see in this graph, the x-axis represents the frequency components present in the signal. Frequency is usually measured in hertz, which indicates the number of cycles per second. The y-axis represents peak velocity of the frequency components. It indicates how much of each frequency is present in the signal. Peaks on the spectrum graph indicate frequencies with high amplitudes. These peaks represent the dominant frequencies or vibration modes present in the signal. In a typical FFT spectrum, specific peaks typically correlate to specific machine faults and related to machine speed. These data is divided into three categories. 1. Sub-synchronous data. 2. Synchronous data. And 3. Non-synchronous data. Now let's understand them one by one. Subsynchronous data refers to vibration signals that occur at frequencies lower than the operating speed of the machinery. Subsynchronous vibrations can indicate issues like bearing defects, foundation problems, or resonance with structural components. For example, consider a rotating shaft with a speed of 1200 revolutions per minute. Any vibration signal that occurs lower than 20 Hz, such as 15 Hz or 10 Hz, these would be considered subsynchronous data. Synchronous data refers to vibration signals that occur at the same frequency as a specific component or rotational speed of the machine. This could include vibrations caused by imbalances, misalignments, bent shaft, looseness, or other faults directly related to the rotational speed of the shaft. For example, consider a rotating shaft with a speed of 1200 revolutions per minute. Any vibration signal that occurs at exactly 20 Hz would be considered synchronous data. Unbalance is the force created by a rotating body when its center of mass is offset from its center of rotation. Unbalance in rotating machinery can occur due to various factors such as 1. Improper assembly. Improper assembly of rotating parts or incorrect installation can introduce unbalance. 2. Material buildup. Accumulation of debris, dirt, or material deposits on rotating parts can disrupt the balance. 3. Wear and tear. Over time, wear and tear on rotating components can lead to changes in mass distribution, causing imbalance. 4. Component damage. Damage to rotating components, such as bent shafts or cracked rotor discs, can create imbalance. Unbalance in rotating machinery exhibits several characteristics, such as 1. High radial peaks at 1 times of shaft RPM. 2. Low axial vibration at 1 times of shaft RPM. 3. Low harmonics of shaft RPM. 4. 1 times of RPM sinusoidal pattern in the time waveform. And 5. It can cause other faults to appear, especially looseness. Misalignment refers to the deviation of the rotating elements from a common center line during operation. This misalignment can occur in various types of machinery, including motors, pumps, compressors, and shaft-driven equipment. Its characteristics includes 1. High axial levels. 2. High axial at 1, 2, and 3 times of shaft RPM. 3. High radial at 1, 2, and 3 times of shaft RPM. 4. Repeatable periodic waveform with 1 or 2 clear peaks per revolution. 5. Phase readings show a 180-degree shift across the coupling. Types of misalignment are 1. Offset misalignment, also known as parallel misalignment, occurs when the rotational axes of two shafts are parallel but not coincident. This misalignment can result from improper installation, thermal expansion, or shaft deflection under load. 2. Angular misalignment, also called slope misalignment, occurs when the rotational axes of two shafts intersect at an angle instead of being parallel. Angular misalignment can arise from improper coupling alignment or shaft bending due to excessive loads. Addressing misalignment requires careful alignment of the rotating shafts using precision alignment techniques such as laser alignment or dial indicator alignment. Looseness refers to excessive movement or play in mechanical components or structures that are intended to be rigidly connected. It alone cannot create vibration, but in the influence of unbalance, misalignment, bearing problems, it amplifies the amplitude. And it should be corrected first. The characteristics of looseness includes 1. Many harmonics of running speed. 2. Directional in nature. Horizontal and vertical amplitudes may differ greatly. 3. Occasional half harmonics. 4. Random, non-periodic time waveform. 5. Broad-based skirts on peaks in the spectrum. Types of mechanical looseness are categorized by 1. Structural looseness and 2. Rotating element looseness. Structural looseness includes looseness of base mount, split casings, bearing caps and bearing supports. Whereas rotating element looseness consists of looseness of impellers, fans, bearings and couplings. Non-synchronous data refers to vibration signals that occur at frequencies unrelated to the operating speed of the machinery. Non-synchronous vibrations may indicate broader structural issues or external disturbances affecting the equipment. For example, these vibrations can result from external sources such as environmental factors, wind, seismic activity, or machinery operating conditions, load changes, gear meshing frequencies. Understanding these characteristics of synchronous, subsynchronous, and non-synchronous vibrations is crucial for diagnosing machinery health and identifying potential faults during vibration analysis. Thank you for listening.